Assalamualaikum dear students. In this lecture we are going to learn how to find the length of an arc of a curve, and this is the section 6.3 of the book, and of course chapter 6 continues. So first of all we'll derive a formula for the length of an arc, and then we'll demonstrate the procedure with the help of examples. If we have a smooth curve, now what is smooth curve? A smooth curve, a function, a function has a continuous derivatives at every point of the interval AB, then such a function is called smooth function, and its graph is called smooth curve. So if we have a smooth curve of the function y is equal to fx, that is its derivative is defined everywhere, and we are required to uh, find the length of this curve. It is this length of this curve in an interval AB. So what is the procedure to approximate this? We will, as always, subdivide this into subintervals. That is, we are going to take a partition of this interval. So at every point we are going to join the points by the lines like this. So we will draw lines to join every two consecutive points on the curve, and then we'll find one of the lengths, and by adding all them up we'll have the length of the whole curve in the interval AB. So let's have a closer look of the line segment in an interval xk minus 1 xk. So this is how it looks like. So this is the curve, and we are going to approximate this length by this line. Now, if we draw perpendicular lines from these points, we have this point xk, f of xk, and then we have this point xk minus 1, f of xk minus 1, right? Or you may say this is yk, and this is yk minus 1. So the length of this interval is delta xk. So we have a right angle triangle here. If we draw a line parallel to x-axis to join this line, and this is the difference between y values, which is called delta yk. So this is delta yk. So what is then the length of this segment? This is equal to delta x by Pythagoras theorem, because this is right angle triangle. So this is equal to delta xk square plus delta yk square square root, right? So this is approximately equal to, we just take delta xk squared common outside 1 plus we have delta yk by delta xk squared. So this is approximately equal to f prime xk by the definition of derivative. In limiting case, this is equal to f prime xk, but otherwise it is approximately. That is why you can see the sign of approximation here. And this is equal to delta xk squared, square root is delta xk. So this is equal to 1 plus f prime xk square, square root times delta xk. Now this is length of one segment. Similarly, we can find the length of every segment, and now adding all these lengths and letting n approaches to infinity, that is number of subinterval is approaching to infinity, then this will lead us to this integral. This is equal to integral from a to b square root of 1 plus f prime x square dx, right? So this is the formula to find the length of an arc in the interval AB and created by the function y is equal to fx. So here is the formal definition. If f prime is continuous, so this is very important condition. We have to remember that while solving the questions related to arc lengths. So if f prime is continuous on the interval AB, closed interval AB, then the length, that is the arc length of the curve from the point A, FA, to the point B, comma, FB is the value of the integral from a to b square root of 1 plus f prime x square dx. And this can also be written as integral from a to b square root of 1 plus dy by dx. So your function is y is equal to f of x, and you are going to differentiate y with respect to x and will integrate with respect to x. Now if some continuity happens, the discontinuity happens, and f prime is not continuous in the interval, then we can try its alternate form. That is, in this case, y is the function of x. Then we will replace this form by x is equal to gy using some manipulations, and then the length of the arc will become L is equal to integral from c to d square root of 1 plus dx by dy square dy. Okay, and the condition here is the same if g prime is continuous. So if both are discontinuous, we are not able to find the arc length using this formula. So in order to use this formula, you have to check this condition. If you find discontinuity in this form, then you can try this form, and even if there is discontinuity in this form as well, then we cannot use this formula, then we have to try something else. So let's solve few questions. Find the length of the graph of fx is equal to x cube over 12 plus 1 over x, where x lies between 1 and 4. That is, a and b are 1 and 4 respectively in this case. So here is the graph of the function. So we have to find this length between the points A and B. Okay. Now what we are going to do, what is the formula? First of all, since the function is smooth in the interval, so we can use this formula A to B 1 plus dy by dx square dx, or you can write a to b square root of 1 plus f prime x square dx. Alright. So in order to use this formula, we have to find the value of 1 plus f prime x whole square. Then we'll take square root. So for this, we are going to differentiate this function first. Now, since this derivative is defined in the interval, so it is important it should be defined in the interval. The points where the function is not derivative is not defined are outside the interval, we don't have any issue. We can use this formula. So this derivative is not defined at x is equal to 0, but this interval doesn't contain the point x is equal to 0. So we are ready to use this form and this formula. So this is f prime x. Now this is 1 plus f prime x square, and after some manipulations we have this result. So the length of the graph over the interval 1 4, we have this by plugging in the values into this formula, and after some calculations we have length of the arc in this interval is equal to 6. Next question. Find the length of the length of the curve y is equal to x over 2 to the power 2 by 3 from x is equal to 0 to x is equal to 2, right? So again, we'll write the formula, and then we are going to differentiate it. So formula, initially we have, since this function is the function of x, that is y is equal to some function of x, so we are going to use dy by dx square dx. Now after differentiation we have this result. Now you can see this is not defined at x is equal to 0. So our interval here is 0, 2, and this is not defined at x is equal to 0, so we are not going to use this form. Now we'll try other form. So for this we have to convert it into the form like x is equal to gy. So for this, y is equal to x over 2 to the power 2 by 3. So we raise it both the sides by 3 by 2. So we have this result, and this leads us to this relation x is equal to 2y to the power 3 by 2. And now we are going to, in order to use this formula, we have to differentiate with respect to y. This is the formula dx by dy square dy. Okay, so we are going to differentiate it with respect to y. And so here is the derivative of the function with respect to y. And what is the limit for y now? Now we are going to check this for limits for y. Y runs through 0 to 2 for this arc of the curve. Sorry, 0 to 1. Yes, 0 to 1. 2 is the value of x. 0 to 1. So this is the closed interval 0, 1, and this function is defined in whole interval. So we can proceed further with this formula. So let's find the limits. Limits are 0 and 1. And now let's plug in the values, and after calculations we have the arc length 2.27. So trick to remember, the total length is the integral of infinitesimal displacement ds along the curve. ds squared in general is equal to dx squared plus dy squared. So ds we can find the displacement by using this result. So ds is equal to square root of 1 plus dy by dx square dx if we have the function y is equal to fx, and this is equal to square root of 1 plus dx by dy square dy if we have function in the form of x is equal to gy. So here we go, this is the result. Okay, next we are going to define a formula for arc length which represent arc length as a function of x. So if y is equal to fx, if f prime is continuous, again this is the condition, so it comes repeatedly, so don't forget this condition while applying this formula. Then by a fundamental theorem of calculus, we can define a new function. Sx is equal to integral from a to x square root of 1 plus f prime t square dt. Okay, so in this case, so we can find the length of the arc for any point uh, in the interval with starting point A. So this is the point to be noted. This is like if we have, so starting point is fixed. If this is A and function is defined and continuous, of course, and its derivative is continuous in the interval B, then we can define the arc length using this formula. At any point, till any point in the interval, right, starting from A. So this is fixed. We can find this piece, we can find the length of this piece. By changing the values, we can find the values of lengths of the arcs. Okay, so if we differentiate this, by fundamental theorem of calculus, derivative of this integral is going to be square root of 1 plus f prime x square, right? So upper limit is x. So we are just going to replace this d by x. So d square dx is equal to 1 plus square root of f prime x square, which is equal to 1 plus dy by dx square. So this is what we discussed in the last slide. From here we have ds is equal to 1 plus dy by dx square root into dx. So let's try and find out the length of arc using this formula. So find the length of the function, same function we are trying. We have already done this in first example, and a, b are same, of course the function is same, and starting and ending points are same, and we have a starting point. 113 by 12 is the starting point. So a here is, if we are going to use the formula just discussed, we need a, that is we need a starting point. So a here is 1. Alright, okay. So what is actually s? S is integral from a to x 1 plus f prime t square dt, right? So for this we have to find the value of f prime 1 plus f prime t square root. So f1 plus f prime square is equal to this, so you can verify this. And by plugging these values into this, we have this, because a is 1, and by solving, now just integrate this, and you have to verify it yourself. Just plug in the values and you will have this result, because this is square, and this squared will give us x squared over 4 plus 1 over x squared, and since this is a function of t, so we have t squared over 4 plus 1 over t squared, and by integrating we have this result. So this is the sx, that is arc length as a function of x. Now what we need to do, we have, in order to find the length in this interval, we have to find s4. Okay, so just replace x by 4 in this formula. So we have the value 6, and you would have noticed that the arc length of this curve in the interval was 6 previously calculated. And that's all for today.